everyone, myself Abhi Patel, and my topic for the presentation is Advanced Algebra Unit 3rd, and I'm from B.sc 3rd year. My roll number is 227057. So what is field? A non-empty set F plus dot is a field if every non-zero element of F has multiplicative inverse. Like for addition, we have these natural numbers can hold closure and associative property but doesn't hold identity and additive inverse. And for all these integers, rationals, real and irrational, they all hold all properties. Now for multiplication, they can hold all the properties instead of additive inverse for natural numbers and integers. Multiplicative identity is always 1 and additive identity is 0. Like for multiplication, multiplicative inverse, example, if we take 5 into 1 by 5 is 1, and additive inverse, if example we take 5 plus minus 5 is equal to 0, that is identity, and the multiplicative inverse identity is always 1. Now to be field, it is necessary to be a group. Now for example, we take Z plus in multiplication is not a field because its multiplicative inverse does not exist. From the previous we have seen for what is vector space. Now let take F plus dot be a field and V be a non-empty set. The element of F are called scalars and the elements of V are called vectors. The V is vector space over the field F. First point is V plus is an abelian group, that is hold a commutative property. V is a closed with respect to scalar multiplication. U belongs to V for every alpha belongs to F. U belongs to V is an external composition. Scalar multiplication and vector addition. Alpha U plus V is equals to alpha U plus alpha V. Alpha plus beta whole bracket V is equal to alpha U plus beta U. Alpha beta whole bracket U is equal to alpha beta U. Now fourth point is 1 into U is U for every U belongs to V, where 1 is the unit element of the field F. Example, vector space R into R is a field. This is an important thing to remember. Z is a subset of Q, is a subset of R, is a subset of C, where this is very important. Field extension. If F is a subfield of a field E, then E is called extension of field F, or simply E is an extension of F. Means if F is a subfield, if there is a field E and F is its subfield, then E is called as extension of field F. Okay. Taking an example, like R is for real is a subfield of Q, R rational. From from previous we have seen C is a subset of R, R is a subset of Z is a subset of Q, Q is a subset of R, and R is a subset of C. And now if from there we can see if E is an extension of F, we denote this flat by the we denote this by this diagram. E is a subset, E is an extension of F. We denote by this. If E is an extension of F, then E is a vector space over field F. We represent this by this too. E bracket F. The dimension of E over F is usually written as E bracket E is to F. Okay, this denotes the dimension of E over F. Now for degree of E over F, let E be an extension of F. Then the dimension of E considered as a vector space over F is called degree of E over F. E is a subset of this represents as F is a extension of E. From here, E is an extension of F, denoted by E is a subset of E. F is a subset of E. This is how we denote the degree of E over F. Now let's see a theorem. Let K be an extension of F and let U belongs to K be an algebraic over F. Let Px be a polynomial of least degree such that Pu is equal to F. Then Px is an irreducible over F. If Gx belongs to Fx is such that Cu is equal to 0, then Px divide Gx. There exists exactly one monoic polynomial Px belongs to Fx of least degree such that Pu is equal to 0. Algebraically closed fields. First is irreducible element. A non-zero element A of an integral domain R with unity is called an irreducible element if A is not a unit, every divisor of A is improper, that is A is equal to BC. Either B is a unit or C is a unit. This is called an irreducible element. A is called an irreducible element, which is not a unit. Prime element, what is prime element? A non-zero element P of an integral domain R with unity is called a pair element. First is P is not unit. If P slash AB, then P by A or P by B is where AB belongs to P. Now what is principal ideal domain? PID, commutative integral domain, in which each ideal is called principal ideal domain. Okay. Now finite extension. What is a finite extension? It is an extension that has a finite degree given two extension L by K and M by L. The extension M by K is finite if and only if both L, K and M by K are finite. Finite, what is finitely generated extension? An extension E of F is called finitely generated extension if there exists a finite number of elements U1, U2 till UR in E such that smallest subfield of E containing F and U1, U2, U3 till UR is F itself. E is equals to F for every U1, U2, U3 till UR. R, C, R field. How? Because R is a subset of C, that is Ri is equal to C. So if we take a C cross is a finitely generated extension in R. Algebraic expression, let K be an extension of F as element A belongs to K is said to be algebraic over F if there exists element A0, A1 to An. There exists n is greater than or equal to 1 is equal to 0. That is A belongs to K is an algebraic over F. There exists a non-constant polynomial Px belongs to Fx such that Pa is equal to 0. That is A is a point of Px. A is a point of Px. Now coming to minimal polynomial, the monoic irreducible polynomial in Fx of which U is a root is called minimal polynomial of U over F. First, we have to it's always exists and it's always unique. Monoic of least degree. Monoic irreducible polynomial should be of least degree and it should be irreducible and U is the root of it. U should be a root of it. Theorem: if every finite extension is an algebraic extension but the converse is not true, means that finite extension is an algebraic extension but the converse means the algebraic extension can't be a finite extension. Okay. Degree of dimension, number of elements in basis and those elements form a set of linearly independent elements. This called degree of dimension. Not all terms are 0. Okay. Matlab, what is the degree of dimension? Number of elements in basis and those elements form a set is called of linearly independent element is called degree of dimension. Theorem: if K is an extension of F, then U belongs to K is an algebraic over F. Implies that Fu is an algebraic extension of F. There is another theorem: let E be an algebraic extension of F and let embedding of E into itself over F, then embedding is onto and hence an automorphism of E. When the embedding is onto, then automorphism happens. Now F homomorphism, let K and L be an extension field of F, then a non-zero homomorphism, hence an embedding. Homomorphism which is non-zero is called an embedding. So, sigma such that K belongs to L such that sigma A is equal to A for every A belongs to F is called an F homomorphism. Sigma K belongs to L such that sigma A is equal to A for every A belongs to F is called an F homomorphism of K into L or an embedding of K in L over F. We show this F homomorphism by this diagrams. A non-zero means sigma 0 is equal to 0 and x is not equal to 0, then sigma x is also not equal to 0, hence kernel of sigma is 0. Kernel consists of those elements whose images are 0. what kernel क्या होता है? Kernel consists of those elements whose images are 0, and the kernel which consists of 0 element, then it's called 1-1 homomorphism. What does it say? That the kernel which consists of 0 element, it's called a 1-1 homomorphism. What is this? Homomorphism and 1-1 is called an embedding. ठीक है? Means that if there is element which is 1-1 also and homomorphism, then it's also called as embedding. Now simple field extension. Let k is equal to f alpha. For some alpha belongs to k, k is an extension of f generated by a single element, then k is called simple field extension of f. It is also called extension obtained by adjunction of alpha to f. Example, C is a simple extension of R, that is RC is equals to C. RI is equal to C, sorry. Theorem, what does this theorem say? Let K be an extension of F of prime. Means that K is an extension of F is of prime, then K क्या है? Simple field extension, then K is a simple field extension. Tower theorem, it's very important theorem. Let F be a subset or equal to E, be a subset of E be a subset and equal to K. Be fields if K ratio E bracket is less than infinity and E ratio F is less than infinity, then K ratio F, K and F is less than infinity, or we can say KE and EF is equal to K and F. Okay, means K ratio E, E ratio F if taken together is equals to K ratio F. Transcendental extension, extension that are not algebraic are called transcendental extension. That is E is extension of F, no element belongs to E, that is algebraic over F, that is no polynomial exists which is having a root in E. For example, Q is a subset of Q pi is transcendental extension. For every pi does not belongs to Q. For every pi does not belongs to Q. This means that this is a transcendental extension. What is characteristics? Characteristic, let F be a field. A positive integer n is said to be a characteristic of F if n is the least positive integer such that n is equal to 0 and A belongs to F. If such an n does not exist, we say F is of characteristic 0. Q, R, C, that is irrational, real and complex, are field of characteristic 0. These Q, R, C, irrational, rational and complex are 0. What is a finite field? Field having finite number of elements, that is known as finite field. Field having finite number of elements is known as finite field. Every field has characteristic either 0 or prime. This is a point to remember. Every field which have a characteristic 0 or infinity or prime. Okay. Every finite field have always finite characteristic. Finite field have always finite characteristics. Finite field always have a characteristic a prime number, say P. Finite field always have a characteristic prime number. This is important, means that a finite field is always having a characteristic prime. Now prime field, any field F is called prime field if it has no proper subfield. Like for that is E is a subset of K is equals to E is equal to F. Sorry, E is a subset of F implies that E is equals to F. Q and Z by P. P are prime fields. Okay. What is there is a note here. Prime field of field F always exists and is the intersection of all subfield of F. This is an important. Like a prime field of field F always exists. Okay, and it is an intersection of all the subfield of F. Okay, that's over now, and thank you for watching my video. Thank you.